This story is about a distance we've grown used to calling nearby. Nearby because among all the vast expanse of stellar space, it truly is one of the shortest. And yet it is measured in light years, not in the ordinary units of our daily lives. About how a person, born under a familiar sky, once wondered, can one travel out there, toward a point that shines steadily and quietly on the southern horizon, and is closer than any other such point in the entire sky? I will speak about what it even means to conceive of such a journey, about the price that must be paid by those who agree to go, about how a person who steps aboard an interstellar ship will most likely never return, and not because engineers will make a mistake, but because the very structure of space leaves no room for such a return, about how the journey to the nearest star is measured in decades, even in the most daring calculations, and in centuries or millennia in more realistic ones, about how this star may have a planet where water could once have existed, and about how between us and it lies not emptiness, as is commonly assumed, but a complex, rarefied, and inhospitable medium through which the ship will travel for years, slowly wearing down and adapting to it, and about how the central question is not, will we go, but who will go and by what means, and why the first to make the journey will most likely not be humans, but tiny probes weighing just a few grams. And what would you do if you were offered a place on such a journey, knowing with certainty that Earth would remain only in memories and in rare signals traveling years in each direction? What matters more, your own life alongside those you love, or participation in what humanity has been doing for hundreds of thousands of years without knowing it could ever say this out loud, stepping out toward another star? Listen, that is what this story is about. The desire to gaze at the night sky and wonder about the nature of distant lights is one of humanity's most ancient impulses. When you understand that each of those points represents a star, possibly with its own planets orbiting around it, a very specific question gradually takes shape. Which is the nearest, and what exactly do we know about it? The answer has not changed in many decades. The star system closest to our own is Alpha Centauri, located in a constellation clearly visible from Earth's southern hemisphere. This is not a single star. The system includes several objects bound by shared gravity. The central pair consists of Alpha Centauri A and Alpha Centauri B, two bodies that resemble our Sun in their main characteristics, though each has its own distinctive mass, luminosity, and spectral class. Somewhat apart from this pair lies a third object, Proxima Centauri, a considerably dimmer star that formally turns out to be the stellar neighbor closest to us. The distance to it is just over 4 light-years, meaning that the light reaching us from it today left that star more than 4 years ago, traveling through interstellar space for a long time before reaching our instruments. On the scale of the galaxy, such a distance is quite small. The diameter of our galaxy spans tens of thousands of light-years, and against that backdrop, 4+ light-years is literally the next block. But on the scale of what humanity possesses technologically, this distance remains practically insurmountable. The fastest spacecraft ever built by humans would take many thousands of years to cover it. Nevertheless, Alpha Centauri has become the starting point for serious discussions about interstellar flight, not because it is easy to reach, but because it is the minimum distance at which it makes any sense to discuss real engineering rather than pure mathematics of the distant future. Interest in this system surged sharply after the discovery of a planet around Proxima Centauri. Astronomical observations confirm the existence of at least one body comparable in mass to Earth. This object was designated Proxima b. Its orbit lies within the so-called habitable zone, the range of distances from a star at which temperature conditions, in principle, permit liquid water to exist on the surface of a solid body. It is important not to overestimate this fact. Lying within the habitable zone does not imply the presence of water, let alone signs of life. It refers only to the temperature range that permits the chemical processes familiar to us on Earth. Subsequently, data emerged about possible additional bodies in this system, but their parameters are still being refined. Astronomical measurements at such distances require exceptionally high precision, and different observational methods often yield slightly divergent results. Science progresses here gradually, step by step narrowing the range of uncertainty. One must consider the nature of Proxima Centauri. This is a red dwarf, a star considerably smaller and cooler than the Sun, yet capable of being quite active. Proxima regularly experiences powerful flares accompanied by bursts of high-energy radiation and streams of charged particles. For a planet in such close proximity to this kind of star, this activity creates difficult conditions. The atmosphere of such a world may gradually be eroded by stellar winds, and its surface may be exposed to intense irradiation. Thus, the question of Proxima B's habitability remains entirely open. Some models show that a sufficiently dense atmosphere, combined with the planet's magnetic field, could provide protection. Others suggest that over billions of years, stellar activity may have stripped the planet of a significant portion of its gaseous envelope. For now, this area contains far more speculation than firm conclusions. And yet the mere possibility of a planet around the nearest star to us fundamentally changed the scientific community's attitude toward interstellar research. Alpha Centauri ceased to be merely an abstract point on the galactic map and became a concrete system with potentially interesting objects. The nearest star to us, and it has a planet comparable to Earth in size. No one yet knows whether there is life there, and it is toward this system that the first interstellar probe will one day be sent, and perhaps a crewed ship as well. But before speaking of routes and engines, a perfectly natural question arises. If we are talking about a crewed mission, who exactly will be its participants, and by what principles is such a decision made? To answer this question, one must first grasp the scale of the task. A flight to Alpha Centauri is not simply the next logical step in space exploration after the Moon and Mars. It is a qualitatively different class of undertaking, incomparable with anything previously attempted. Even using technologies that currently exist only in theoretical calculations and provide speeds representing a significant fraction of the speed of light, the journey would take several decades. With more realistic approaches available today, we are talking about centuries or millennia. This means that the classic expedition model, where a crew departs, completes its objectives, and returns to Earth within a single human lifetime, is fundamentally inapplicable to interstellar travel. From this constraint emerge several fundamentally different concepts. The first is a generation ship, on board which several generations of people succeed one another during the journey. Those who remember Earth gradually give way to those for whom metal bulkheads and artificial light are the only reality they have ever known. The second concept envisions deep hibernation, in which the biological processes of the body slow to the point where the subjective experience of flight time is considerably shorter than the objectively elapsed duration. The third is a fully automated mission, where all the work is performed by artificial intelligence without any human presence on board. Each of these approaches carries fundamental limitations. A generation ship requires a stable, closed ecosystem capable of functioning without external supplies for centuries. Long-term human hibernation technology is currently at the earliest stages of research, and the question of whether the associated biomedical problems can be solved remains open. Fully robotic missions eliminate biological risks, but deprive the project of a living human presence. The conversation about who will fly to Alpha Centauri logically begins not with compiling a list of candidates, but with defining the architecture of the mission itself. First comes the decision about the type of expedition, and only then are requirements formulated, for people or for control systems. If a crewed mission is considered, the priority qualities that emerge are far from those traditionally associated with the image of a pioneer. Of paramount importance are psychological resilience to years of isolation, the ability to live productively in an extremely confined space, and the capacity to maintain complex technical systems without outside help for a very long time. Studies in space psychology clearly show that even multi-month expeditions on orbit or in ground-based deep space simulators place serious strain on carefully selected specialists. An interstellar flight will multiply these difficulties. What becomes critical here is not only physical health and professional skill, but also social compatibility. The ability to resolve conflicts within a small group without any outside support, and the ability to maintain motivation in the complete absence of familiar reference points. The task of selecting participants for an interstellar expedition turns out to be, first and foremost, social and biological, and only then technical. For a generation ship, an additional layer of questions arises concerning genetic diversity. If several generations are to succeed one another on board during the journey, the initial group must be large enough to avoid accumulation of harmful mutations and preserve the adaptive potential of the population. Estimates of the minimum necessary size vary depending on the assumptions made, but almost all calculations involve hundreds or thousands of people. This is no longer an expedition in the conventional sense. It is a small city moving continuously through the darkness of interstellar space, sustaining within itself all the complexity of human society. Alongside discussions of crewed missions, scenarios involving compact automated probes are actively debated. One of the best-known approaches envisions the use of ultralight craft accelerated by powerful laser installations to a significant fraction of the speed of light. Such devices could reach the Alpha Centauri system within several decades and transmit data back to Earth. This idea has moved beyond pure theory. Materials for light sails are being studied, schemes for laser arrays of sufficient power are being developed, and methods of communication across interstellar distances are being investigated. This is not a ready technology, but an active field of engineering research, gradually bringing the concept closer to practice. The question of who will fly to Alpha Centauri is inseparable from the question of how they will get there. For automated missions, the answer lies in algorithms and instruments. For crewed ones, in a complex combination of biological, psychological, and cultural criteria. In both cases, Alpha Centauri serves not only as a concrete destination, but also as a model system for thinking through all future interstellar projects. Before choosing people or programming automation, one essential question must be answered. How long will the journey actually take? And does physics allow it to be made reasonably short? Understanding interstellar travel begins with the very nature of distance. Interstellar space does not resist movement the way air or water does, but it obeys strict physical laws. Above all, the law of the finite speed of propagation of information and energy. Light moves faster than anything in existence, and no material object can exceed this limit in accordance with the principles of special relativity. The distance to Alpha Centauri is expressed in light years precisely because kilometers lose their clarity here. 1 light year is the distance a ray of light travels in 1 Earth year. To Alpha Centauri, it is just over 4 such units. If converted to conventional units, the result is a number with 13 zeros in kilometers, a magnitude that is practically impossible to hold in the imagination. This is why engineers and astronomers prefer to work with travel times at various speeds. The fastest spacecraft ever created by humanity left the solar system at speeds on the order of tens of kilometers per second. At that rate, the journey to Alpha Centauri would take tens of thousands of years, a span exceeding the entire documented history of human civilization. This immediately makes clear that talk of interstellar missions is only possible in the context of fundamentally different technologies, since everything that exists today is clearly unsuitable for this purpose. Modern rocket technology is based on the reactive principle. Ejecting mass in one direction creates thrust in the opposite direction. This method works excellently for travel within the solar system, but for interstellar distances, it runs into a fundamental limitation. The higher the required speed, the greater the fuel reserve that must be carried along. The mass of the fuel increases the total mass of the ship, which in turn requires even more fuel for acceleration, a vicious circle from which there is no escape using chemical reactions. Nuclear thermal engines, which use the energy of heavy nucleus fission to heat a working fluid, offer a certain efficiency gain over chemical systems, but only by a factor of several, which is useful for interplanetary travel and wholly insufficient to achieve a meaningful fraction of the speed of light. This is precisely why the scientific literature examines alternative concepts in detail. One of the most thoroughly developed is the thermonuclear engine, in which energy is released by the fusion of light atomic nuclei, for example, isotopes of hydrogen. This is exactly the process that powers the light of stars, including our own sun. On Earth, controlled nuclear fusion remains an experimental technology, but theoretical calculations convincingly show that it can achieve significantly higher ejection velocities for the working substance. In designs for interstellar ships with thermonuclear propulsion, directed micro-explosions or continuous reactions are envisioned to create a powerful plasma flow. The Daedalus and Icarus concepts were developed as detailed engineering models to test the feasibility of this approach. Results show that with a sufficiently large ship and corresponding fuel reserves, it is possible to achieve several percent of the speed of light. The journey to Alpha Centauri at that rate would take several decades, a span that already fits within a single human lifetime. Outstanding issues remain: reactor stability, the required fuel mass, and protection of the crew from the radiation that inevitably accompanies thermonuclear reactions. Another direction involves antimatter. When annihilation occurs, the meeting of a particle of matter with its corresponding antiparticle, the entire combined mass is converted into energy. This is theoretically the most efficient of all known methods of extracting energy from a finite amount of matter, and an antimatter engine could accelerate a ship to very high speeds while using comparatively little fuel. The practical problem is that producing antimatter requires enormous energy expenditure, and storing it in any meaningful quantity remains far beyond current technical capabilities. Particle accelerators can produce antimatter only as individual particles, which can be held in special magnetic traps for only very short periods. Antimatter engines therefore exist currently only as a field of theoretical research, helping to understand the physical limits of what is possible, but not considered a foreseeable engineering prospect. A fundamentally different path is offered by the concept of external acceleration, in which the ship does not carry the primary energy source on board. Instead, momentum is transferred to it from outside. The most well-known example of this approach is the light sail. This is a thin, reflective structure onto which a powerful beam of laser radiation is directed from Earth or from an orbital platform. Photon pressure at sufficient intensity, combined with the low mass of the craft, is capable of accelerating it to significant speeds. The primary energy burden remains in the solar system rather than being carried on board. This removes the vicious circle limitation of fuel mass that makes chemical rockets unsuitable for interstellar distances. The Breakthrough Starshot project is implementing exactly this idea. Miniature probes weighing a few grams are accelerated by ground-based laser arrays of enormous power to a significant fraction of the speed of light. According to calculations, such craft could reach the Alpha Centauri system within several decades and transmit back the first images of that system. This is not a crewed mission. It is reconnaissance. Tiny cameras and sensors capable of giving humanity, for the first time, a direct view of a neighboring star system from relatively close range. The laser installation needed to accelerate such probes is comparable in scale to a small city. Currently, ultra-thin materials for light sails, resistant to heating and deformation in a powerful laser beam, are being studied. Phased laser array configurations capable of maintaining a directed beam on a rapidly receding target are being developed. Trajectory stabilization methods are being examined. These are experimental steps, but the physical principles are well understood. Theoretical works also mention more exotic ideas: warp fields, wormholes, curvatures of space-time. These concepts draw on mathematical solutions to the equations of general relativity and in principle permit movement between distant points faster than a ray of light would traverse that path in the usual way. However, such structures require forms of matter with negative energy or other exotic properties not observed in nature. These approaches therefore remain at the level of mathematical reasoning, while practical engineering is focused on what the known laws of physics permit. A separate problem is deceleration at the destination. Accelerating a ship is only half the task. For the craft to enter the Alpha Centauri system and begin observations, rather than fly through it in a matter of hours, its speed must be reduced. Magnetic sails interacting with interstellar plasma are being considered, as is the use of light pressure from the destination star itself. All of these schemes require precise calculations and long-term system reliability. An interstellar engine must function for years or decades without maintenance, enduring radiation exposure, micro-impact damage, and temperature swings. Accelerating even a comparatively small ship to a significant fraction of the speed of light requires an amount of energy comparable to the annual output of the entire modern civilization. This does not make the task fundamentally impossible, but it underscores its scale. This is precisely why scientific publications note that the first actual missions to Alpha Centauri will most likely be automated in miniature. They will serve as scouts that clarify the parameters of the interstellar medium and provide the first direct images of the neighboring system. Only after that will there be substantial grounds for discussing projects of an entirely different scale. The distance between stars teaches patience. It compels thinking not in terms of individual launches, but in horizons spanning generations. But before thinking about engines and people, one must understand exactly what the ship will have to fly through. Interstellar space seems like absolute emptiness, and that is an illusion. In reality, the space between stars is filled with rarefied matter and permeated by fields and radiation. For a flight to Alpha Centauri, this medium becomes as much a participant in the mission as the engine or navigation system. Understanding its properties is just as necessary as calculating the trajectory. The basis of the interstellar medium is hydrogen. On average, only a few atoms per cubic centimeter are present, and in some regions even fewer than one. By terrestrial standards, this is nearly a perfect vacuum. Yet on scales of light years, even such rarefied matter acquires practical significance for any moving object. A ship traveling at high speed continuously collides with these particles, and each such encounter carries kinetic energy. In addition to hydrogen, the interstellar medium contains helium and trace amounts of heavier elements. Some atoms are in a neutral state, others are ionized. In some regions, they gather into clouds. In others, they are distributed nearly uniformly. Between the stars, microscopic dust grains are also found, particles of silicates, carbonaceous compounds, and water ice, fractions of a micron in size. At high relative speeds, even these become a significant damage factor. Current data on the interstellar medium comes from several sources. Spectroscopy of distant objects allows the chemical composition of gas clouds to be determined. Radio observations of neutral hydrogen at a wavelength of 21 centimeters provide a map of matter distribution. Direct measurements are taken by probes that have already passed beyond the boundaries of the solar system. The Voyager series of spacecraft became the first man-made objects to reach interstellar space, and they continue to transmit data on plasma density, magnetic fields, and particle fluxes. These measurements show that the local interstellar medium in the vicinity of the Sun is relatively calm but inhomogeneous. The first direct data from interstellar space is no longer theory. The Voyager probes for the first time allowed measurement of what previously could only be hypothesized on the basis of remote observations. The temperature of interstellar gas varies across a very wide range. In cold neutral clouds, it is only a few tens of degrees above absolute zero. In heated regions associated with supernova remnants or active radiation sources, the gas is heated to thousands and even millions of degrees. On the anticipated route to Alpha Centauri, current models suggest comparatively warm and rarefied regions predominate, although the precise structure of the medium remains an active area of research. Magnetic fields are another constant component of this medium. Weak by terrestrial standards, they extend over enormous distances and influence the motion of charged particles. For a traveling ship, this means a continuous flux of galactic cosmic rays, high-energy protons and atomic nuclei arriving from our own galaxy, as well as from considerably more distant sources. These particles can penetrate structural materials and affect both electronics and biological tissue. Radiation shielding becomes one of the central engineering challenges for any interstellar craft. For automated probes, a combination of shielding and redundancy of critical systems is employed. For crewed missions, the task is significantly more complex. A layer of protective material is needed that is sufficient to attenuate radiation fluxes, yet not so heavy as to make the structure impractical. Designs involving water, polyethylene compounds, and magnetic shields creating an artificial protective field around habitable compartments are under consideration. Space radiation is dangerous not only through acute, immediate effects, but also through accumulated long-term exposure. Years or decades of continuous irradiation increase the risk of mutations, cancer, and disruptions to the nervous system. The experience of orbital stations and interplanetary missions provides only a starting point for assessing these risks, and interstellar flight involves incomparably longer durations. No less significant is the problem of micrometeoroids and dust. At speeds representing a noticeable fraction of the speed of light, even a particle with a mass less than a grain of sand carries kinetic energy comparable to that of an artillery show. The designs of interstellar craft envision multi-layer protection, a forward shield, intermediate layers, and systems for distributing impact energy. For small probes, an option is a single-use outer layer that gradually ablates, absorbing the impacts. Navigation in interstellar space has its own specific character. Near Earth, orientation is performed using stars and radio signals. At distances of light years, the radio beacons of the solar system become too faint, so autonomous methods are being developed. Among them, the use of pulsars as natural navigational beacons deserves special attention. These rapidly rotating neutron stars emit strictly periodic pulses, whose stability is comparable to that of the finest atomic clocks. The uniqueness of each pulsar allows the three-dimensional position of the ship in space to be determined from several such sources with high precision, without any communication with Earth. Inertial systems and observation of background objects supplement pulsar navigation, while modern algorithms allow stellar field positions to be compared and the course corrected without external commands. For missions with multi-year flight times, such autonomy is absolutely critical. Any response from the solar system will arrive with a delay of several years. A separate aspect is the thermal regime of the craft. Interstellar space is cold, but the ship carries its own heat sources: electronics, power installations, habitation modules. In conditions of near-perfect vacuum, the only available means of dissipating excess heat is thermal radiation. This imposes constraints on the layout of the craft and requires significant radiating surfaces, which affects both the form and mass of the structure. Speaking of living systems on board, another level of complexity is added. Biological organisms are sensitive not only to radiation, but also to the absence of familiar diurnal cycles, to isolation, and to a closed ecosystem. All these factors combine into a single picture. The flight to Alpha Centauri is not a journey through emptiness, but through a complex, if rarefied, medium that slowly and continuously interacts with the ship. This is precisely why preparation for interstellar missions inevitably begins with a thorough study of the space between stars. The medium is understood in its broad outlines. The next question is, how exactly to organize life on board a ship that will be traveling toward its destination not for a year or two, but for several decades straight? Understanding interstellar travel takes on a new dimension if the ship is perceived not as a vehicle, but as an independent ecosystem. For a mission to Alpha Centauri, this is especially important. The issue is not a temporary period of isolation, as on an orbital station, but prolonged existence in a wholly artificial environment where every element, the air, the water, the food, the composition of the microbiome, and the psychological state of the people must remain in stable equilibrium for decades. On Earth, life is sustained by a vast system of material exchange among the atmosphere, oceans, soils, and living organisms. In a spacecraft, all of this must be compressed into the volume bounded by the hull. An interstellar ship is a small biosphere obliged to function without a single failure for several decades in a row, with no possibility of obtaining anything from outside. Such a system is called a closed life support environment, and its defining characteristic is the near-complete absence of external resources. Everything the crew has must be continuously recycled and returned to the cycle. Modern orbital stations already use elements of such systems. Water undergoes multi-stage purification and becomes drinkable again. Carbon dioxide is removed from the air and partially recycled. Oxygen can be generated by electrolysis of water. These technologies function, but in their current form require regular maintenance and periodic supplies of consumables from Earth. For an interstellar ship, such an approach is fundamentally unacceptable. Stocks must be either truly enormous or fully self-renewing within the system itself. This entails a transition to bioregenerative schemes, in which plants, algae, and microorganisms play the key role. Plants perform multiple functions simultaneously. They produce oxygen through photosynthesis, absorb carbon dioxide, participate in water purification, and provide part of the crew's diet. Experiments show that closed plant modules can function stably for many months. However, extrapolating these results to the scale of a multi-year flight remains an open research task. It is not known how minor imbalances accumulate over such long periods, or which failures might prove critical. One specific challenge is ensuring complete and varied nutrition. The human body requires not only calories, but also a wide range of vitamins, minerals, essential amino acids, and trace elements. A single crop cannot supply everything needed, so systems involving multiple species of plants, fungi, and possibly insects as a source of high biological value protein are being examined. Such projects are studied in ground-based, isolated experiments, where small groups of volunteers live in fully closed complexes, simulating the conditions of long-duration missions. These studies have revealed an important point. The stability of an ecosystem is determined not only by biological factors, but also by the behavior of the people maintaining it. Even minor deviations in the care regime for plants or the distribution of resources can, over time, lead to the accumulation of problems that in a closed environment have no tendency to smooth themselves out on their own. Every mistake here has the property of amplifying. Particular attention is paid to the microbiome. A person carries an enormous number of microorganisms, which rapidly colonize all surrounding surfaces. Under normal terrestrial conditions, the diversity and openness of the environment constrains the growth of individual bacterial species. In the confined space of a ship, this balance can shift. Certain microorganisms reproduce more actively under microgravity conditions, form persistent biofilms, and can damage structural materials. Air and water purification systems must therefore account for not only chemical, but also biological processes, and monitoring the microbiological composition of the environment becomes a constant task for the crew. The question of gravity is directly connected to the long-term health of people on board. Prolonged weightlessness leads to bone mass loss, muscle atrophy, and changes in the cardiovascular system. For a journey lasting several decades, such effects are entirely unacceptable. This is precisely why rotating habitat modules appear in almost all interstellar ship designs. The centrifugal acceleration experienced by the body in such a section is perceived as gravity. Modeling shows that even a load somewhat less than Earth's can substantially slow bone mass loss and support cardiovascular function. It is important that the radius of rotation be sufficiently large. At small radii, unpleasant effects arise from Coriolis forces, dizziness, and disorientation that undermine crew performance. Even with artificial gravity, the problem of confined space remains. Humans evolved under open skies. With stable gravity, cycles of day and night, a rich sensory world, and freedom of movement. Placed in a sealed metal hull for decades, the organism faces a burden for which evolution simply had no time to develop adaptations. Psychological studies of long-duration isolation, an important component of preparation for deep space missions, examine the experience of polar station personnel, submarine laboratory crews, and participants in specialized isolation experiments. Observations consistently show that over time, people in conditions of prolonged isolation can develop sleep disturbances, diminished motivation, heightened irritability, and difficulties in interpersonal communication. An interstellar flight multiplies all these effects, making the psychological resilience and social compatibility of the crew just as much an engineering challenge as engine reliability or radiation shielding. These effects rarely manifest immediately. They accumulate gradually as the organism exhausts its adaptive reserves. This is precisely why psychological support programs become just as integral a part of the project as engine design or the life support system. Among the key tools, a structured daily routine that creates predictability and reduces anxiety. Regular physical exercise that sustains not only the body, but also emotional equilibrium. Thoughtfully designed private spaces where each crew member can be alone. Communication with Earth, even with inevitable delays, preserves a psychologically meaningful connection with the home planet. The use of virtual environments is also being considered, capable of simulating changing landscapes, expanding subjective space, and giving the mind the sense of novelty that is so lacking in the monotonous routine of shipboard life. The social structure of the crew is no less important than any technical module. A small group of people will exist together for many years, with no possibility of changing their surroundings or stepping outside the metal bulkheads. This places demands on the selection of participants that go far beyond professionalism. Personal compatibility, readiness to cooperate under stressful circumstances, and the ability to resolve conflicts without an outside mediator play the key role. Physical health and technical competence are only part of the criteria. Temperament, reactions to monotony, and the ability to maintain group cohesion under prolonged pressure are assessed with no less rigor. If one considers scenarios extending beyond a single human lifetime, the question of generationships inevitably arises. In such a scenario, part of the crew is born during the flight itself, and these people will never see Earth, nor the star-filled sky of their home planet. Only artificial light, bulkheads, and the gradually changing faces of those who share the journey with them. They face questions fundamentally different from engineering ones. How to build education in an entirely closed environment. How identity forms in a person for whom the ship is the only world they have ever known. How the sense of the mission's purpose is transmitted to those who never chose it for themselves. These themes are actively researched across adjacent fields of knowledge, from pedagogy to bioethics, but no definitive answers yet exist. The technical side of this whole system is inseparable from its human dimension. Every automated circuit requires oversight. Every biological environment is subject to unpredictable changes. This is precisely why the interstellar ship is conceived as a hybrid construction in which machines and living organisms form a single, interdependent cycle of life support. In such a system, redundancy is critical. If one node fails, another must immediately take over its functions. This complicates and adds mass to the design, increases its cost, but without such an architecture, long-term stability is unattainable. The ship's ecosystem is not a static construction, but a continuously evolving process. Over time, it will change under the influence of radiation, microbial mutations, and the people themselves. The task is not to create a perfect, sealed microcosm, but to ensure its capacity to adapt without losing its key functions. In this sense, the interstellar arc becomes an experiment in transporting a fragment of Earth's biosphere into deep space, a test of how far life in the forms familiar to us can exist outside its home planet, relying solely on knowledge, technology, and careful attention to the fragile balance between biology and engineering. The ecosystem is calibrated, but there is a threat that cannot be hidden behind bulkheads or shielded by green leaves: ionizing radiation penetrating any material in its path. A dust particle fractions of a micron in size, at an encounter velocity of several percent of the speed of light, is no longer merely dust. It is a micro-projectile carrying kinetic energy comparable to an artillery shell. Over the course of a single interstellar flight, thousands of such collisions will occur. The interstellar medium appears to be emptiness, but this is a deceptive impression. For a ship moving at high speed, it becomes a ceaseless stream of impacts. Among these, ionizing radiation holds a special place, arriving simultaneously from several sources. Galactic cosmic rays are born in supernova explosions and other powerful astrophysical processes. Charged particles are also emitted by stars, including the Sun. Finally, secondary radiation arises when primary particles collide with the ship's own hull. In orbit around Earth, a significant portion of this flux is blocked by the planet's magnetic field. In interstellar space, there is no such shield, and the crew is under constant bombardment by particles of enormous energy. They can damage DNA, trigger mutations, accelerate tissue aging, and disrupt microprocessors. Measurements from automated probes in crewed stations show that even over several months outside the magnetosphere, a person accumulates a notable radiation dose. A simple extrapolation of these data for a flight lasting decades points to a serious problem. The most direct approach to shielding is passive. Thick layers of material absorb some of the particles, attenuating the flux. Metals stop radiation effectively but are heavy. Hydrogen-containing materials, water or specialized polymers, work better against certain types of particles and can simultaneously serve additional functions in the life support system. This is precisely why water is considered a multi-purpose resource in some designs. It serves for drinking and for watering plants, while simultaneously being positioned in the walls of habitable compartments to form a protective belt. The tanks of fuel and other working substances can serve a similar role, allowing multiple tasks to be combined without excessive increase in the overall mass of the structure. Active shielding methods are also being studied in parallel: magnetic and electrostatic screens that create fields deflecting charged particles. In principle, this resembles Earth's magnetosphere, recreated in an artificial and compact form. The main difficulty here is power consumption and stability. To create a field of sufficient strength around a large ship, significant power is required, together with complex infrastructure of superconducting circuits operating reliably for decades. A separate line of research is biological radiation resistance. Organisms possess mechanisms for repairing damaged DNA, and scientists are studying whether these processes can be enhanced by pharmacological or genetic methods. For now, this remains an area of laboratory experiments and theoretical models. Microscopic dust particles form another layer of threat. At relativistic speeds, a dust particle fractions of a micron in size carries kinetic energy comparable to the impact of a miniature projectile. Multi-layer shields are proposed for protection, where the first layer vaporizes the particle and subsequent layers absorb the resulting plasma. Some concepts envision creating a rarefied gas or plasma cloud ahead of the ship's nose as a buffer. Particles entering it lose energy before making contact with the hull. Implementing this approach requires a constant expenditure of matter and precise control of the shape of the protective front. Radiation also affects electronics. Modern microchips are vulnerable to individual charged particles capable of causing faults or irreversible damage. So critically important computing units are duplicated and software continuously checks data integrity. Route selection itself becomes a tool of protection. The density of the interstellar medium is inhomogeneous, and astronomical maps allow trajectories to be charted through comparatively clean regions of space. These maps are continuously refined on the basis of data from telescopes and interplanetary probes. At this level of design, navigation becomes not merely a geometric task, but also a physical one, requiring account of particle distribution, the direction of magnetic fields, and possible surges of stellar activity. The ship must not simply follow a set course, but continuously measure the parameters of its surrounding environment and adapt its configuration in response. Autonomous radiation monitoring systems will be able to redistribute protective resources, relocate the crew to better shielded compartments during heightened activity, and adjust the operating modes of sensitive instruments. A signal from Earth will take years to arrive, and most decisions will have to be made on board, relying on pre-programmed algorithms and local measurements. This requires advanced, reliable, autonomous control systems capable of acting under conditions of uncertainty. Taken together, radiation and the interstellar medium form a constant background throughout the entire flight. Not one-time obstacles, but a continuous presence demanding unceasing attention from engineering systems and biological adaptation mechanisms. Protection against these impacts is distributed throughout the entire structure of the ship, from the layout of compartments to the choice of materials and the logic of the control system. In this way, the image of the interstellar arc gradually emerges, not as a hermetically sealed capsule isolated from the universe, but as a dynamic system in continuous interaction with it. A system for which the space between stars becomes an active participant in the journey, influencing every decision and every design line. Radiation can be shielded with varying degrees of effectiveness. But how does one supply the crew with food for decades to come when no delivery from Earth will ever follow? Children born on an interstellar ship will never see Earth. For them, home is the metal walls, the hydroponic beds, and the rotating habitation sections. What it means to be human in such a world is a question without ready answers. But before it confronts them in full, the ship must solve a far more down-to-earth problem, feeding people throughout the entire journey. The basis is the principle of a closed biological cycle. Exhaled carbon dioxide is converted back into oxygen. Used water is purified and returned to circulation. Organic waste is processed into nutrients for plants or microorganisms. Elements of such systems are already partially implemented on orbital stations, where air and water purification units are used, and experimental plant modules supplement regenerative cycles. However, an orbital station receives regular deliveries from Earth. An interstellar ship is fundamentally deprived of this possibility, and the degree of system closure must be considerably higher. Plants occupy a central place in such a scheme, performing multiple functions simultaneously. They participate in gas exchange, absorbing carbon dioxide and producing oxygen. They serve as a food source. And, what is often underestimated, they have a marked psychological effect on the crew, creating the sense of a living environment in a place where everything else is made of metal and plastic. Studies in isolated ground-based complexes confirm that even small green zones reduce stress levels and help stabilize emotional states. which is especially important during prolonged isolation with its inevitable monotony. Hydroponic and aeroponic methods, in which the roots receive a nutrient solution or aerosol instead of soil, already demonstrate their viability in orbit. Several species of grains and vegetables can yield stable harvests in limited space. For an interstellar flight, such systems require scaling and an expansion of variety, since a balanced diet requires adequate content of proteins, fats, carbohydrates, vitamins, and trace elements. A single crop will not meet this task. Part of the food will likely be produced using microbiological processes. Algae and specially selected bacteria are capable of synthesizing complete protein from simple chemical compounds, significantly expanding the capabilities of the ship's food production system. Organic residues, inedible parts of plants, and human waste products enter bioreactors, where microorganisms break down complex substances into simpler ones, returning nitrogen, phosphorus, and carbon to the production cycle. This process resembles the workings of Earth's soil ecosystems, with the difference that here it takes place in strictly controlled reservoirs with specified environmental parameters. Water in this system becomes one of the most valuable resources on board. It circulates among people, plants, and technical systems, undergoing multi-stage purification, including removal of dissolved salts and organic impurities. With adequate reliability of such circuits, the same volume of water can be used repeatedly, replenishing only the minimal, inevitable losses. The microbiological balance requires no less careful attention. In a closed environment, any shifts in microbiome composition spread quickly, so continuous monitoring of bacteria and fungi in the air, on surfaces, and within technical systems becomes a routine task for the crew. Filters, ultraviolet irradiation, and antimicrobial coatings suppress the growth of unwanted organisms, but only with continuous oversight. Life in such a space is not only biology, but also psychology. Prolonged isolation, a limited social circle, and the absence of familiar stimuli place a burden on the psyche that has no equivalent in terrestrial experience. The ship's architecture is designed with this in mind. Variations in lighting that simulate the change of day and night, color schemes that create a sense of spaciousness, personal zones where each person can withdraw, areas for shared activities and rest, virtual environments, audio recordings, visual landscapes, interactive spaces, give the mind the opportunity to switch between stimuli, simulating the variety that is absent in reality. Neuropsychological models show that a sense of control over one's environment and the predictability of events significantly reduce stress levels. This is taken into account in the design of both the ship and the preparation programs for the crew. Crew leadership is selected with particular care, and not only by professional criteria. Personality traits, capacity for cooperation, and tolerance for uncertainty are taken into account. Simulations of long-duration missions allow assessment of how a specific individual responds to monotony and limited social contact. On the basis of these data, crews are assembled in which differences in temperament complement each other, creating a stable group. Preparation includes not only technical skills, but training in communication, self-regulation, and the maintenance of group cohesion. Because in this journey, social stability is no less important than engine reliability. For scenarios extending beyond a single lifetime, the closed ecosystem ceases to be merely a set of technical modules. It becomes an artificially created world in which physics, chemistry, biology, and human relations are intertwined. The interstellar arc in this context is no longer a vehicle, but an independent habitat whose stability is determined by the coordinated workings of many cycles, from molecular processes in bioreactors to the subtle psychological mechanisms within the crew. It is precisely in this complex equilibrium that the possibility of a long journey between stars is born. The crew is fed, the biosphere is functioning. One final challenge remains: How does the ship determine its exact position in interstellar space when GPS is unavailable, and any request to Earth returns with a delay of several years in one direction? Dead neutron stars turn out to be the finest navigational beacons in the universe. The rhythm of pulsars is more accurate than any atomic clock, and it is they who will ultimately show the interstellar ship its course through the darkness between the stars. In Earth's vicinity, navigation relies on radar measurements, satellite navigation signals, and optical observations. In interstellar space, all these reference points disappear. Distances are measured in light years, and familiar beacons become too faint to serve as reliable guides. The basis of orientation becomes astronomical navigation. The position of the craft is determined from the angular distances between bright stars, the spectral characteristics of radiation, and the apparent displacement of objects against the background of distant galaxies. In principle, this resembles the maritime navigation of past centuries, only the scale is incomparably greater, and the precision requirements are far higher. Pulsars hold a special place in this system. These rapidly rotating neutron stars emit strictly periodic pulses of radio waves or X-ray radiation, unique to each source and stable with a precision comparable to that of the most advanced atomic clocks. From the arrival delays of signals from several such objects, the three-dimensional position of the ship in space can be calculated without any communication with Earth. Such systems are already being tested in near-Earth missions, and experimental installations confirm that autonomous pulsar navigation is technically feasible. For an interstellar ship, this is especially important. Real-time control from the home planet becomes impossible given multi-year signal delays. Communication with Earth becomes a separate engineering challenge. Radio waves attenuate with distance, and as the ship recedes, even powerful transmitters produce an ever weaker signal. Laser communication systems capable of transmitting information in a tightly directed beam are being examined, concentrating energy and substantially increasing range, but requiring exceptionally precise pointing, since the slightest angular deviation at interstellar distances becomes an enormous miss. But even with laser communication, signal delay remains inescapable. The distance to Alpha Centauri is such that a message takes several years in one direction. Every exchange of information becomes a slow dialogue through years, and the crew is forced to make most decisions autonomously, drawing on pre-established protocols and their own observations. Navigational calculations are further complicated by the fact that the ship is moving at a notable fraction of the speed of light. At such speeds, effects of special relativity begin to manifest. To an outside observer, time on board passes more slowly, and for the crew, the picture of the external universe appears altered. These differences must be accounted for in clock synchronization, maneuver planning, and the interpretation of incoming signals. The control system must continuously recalculate coordinates, accounting for relativistic corrections, using complex mathematical models that link the readings of the ship's internal clock to the timescale of the external reference frame. An accumulating error in these calculations at interstellar distances can become critical. Inertial navigation, measuring accelerations and rotations using gyroscopes and accelerometers, allows movement to be tracked without external reference points, but inevitably accumulates errors over time. Therefore, its data are regularly cross-checked against astronomical observations, preserving accuracy over many years. The orientation of the ship is important not only for navigation. A sail driven by laser or stellar radiation must precisely maintain its position relative to the energy source, and radiators dissipating excess heat must be directed so as to radiate it into space effectively. All of this is integrated into a unified automated control system that analyzes streams of data from many sensors, predicts the trajectory years ahead, and proposes optimal solutions. Artificial intelligence in this context serves not as a replacement for the crew, but as a support tool capable of processing volumes of information beyond human perception. At the same time, The principle of algorithmic transparency remains mandatory. The people on board must understand the logic of decisions made by the system. This reduces the risk of errors and sustains trust in the automation. Interstellar navigation becomes a synthesis of astronomy, physics, mathematics, and engineering. It rests on the stability of pulsars, the geometry of stellar fields, the accuracy of internal clocks, and the robustness of computational models, gradually advancing the ship through space where familiar reference points yield to abstract coordinates and the rhythms of distant neutron stars. Navigation is working. One final mystery remains. Will the human body and psyche withstand decades of such conditions? And what exactly happens to an organism deprived of everything for which evolution shaped it? The human body took shape over millions of years under open skies, with stable gravity, cycles of day and night, a rich sensory world, and freedom of movement. Placed in a sealed metal hull for decades, it faces a burden for which evolution simply had no time to develop adaptations. The first and most obvious consequence is the loss of bone mass and muscle tissue under reduced gravity. Orbital stations provide extensive observational material here. Even with daily workouts on specialized training equipment, bone tissue loses density and muscles shrink in volume. These processes are only partially reversible and require constant prevention. This is precisely why rotating habitation modules appear in almost all interstellar ship designs. The centrifugal force acting on the body in such a section is perceived by it as weight. Modeling shows that even a load somewhat less than Earth's can substantially slow bone mass loss and support cardiovascular function. It is important that the radius of rotation be sufficiently large. At small radii, unpleasant effects arise from Coriolis forces, dizziness and disorientation that undermine crew performance. The radiation dose accumulated over decades constitutes a separate medical problem. Beyond Earth's magnetic field, the crew is continuously exposed to cosmic rays and high-energy particles. Long-term irradiation increases the risk of cancer and nerve tissue damage, risks that orbital experience allows only approximate estimation of. The response lies not only in structural protective measures, but also in biomedical approaches. Continuous monitoring of DNA damage, individualized recovery protocols, pharmacological support. All of this requires flexible medical systems capable of functioning autonomously without connection to terrestrial clinics. The microbiology of the closed environment adds yet another level of complexity. The ship is an ecosystem in which humans, bacteria, and fungi coexist in a confined volume. And long-term observations show that the microbial composition of air and surfaces inevitably changes over time. Certain microorganisms become more resistant, form biofilms, and may damage structural materials. Air and water purification systems are designed with this long-term dynamic in mind, and the crew undergoes regular preventive procedures. The psychology of prolonged isolation remains one of the least studied, yet most important, areas of preparation for long-duration missions. People in closed groups, on polar stations, submarines, in specialized isolation experiments, consistently encounter sleep disturbances, mood swings, and reduced cognitive flexibility. In an interstellar flight, these effects may be amplified by the fundamental impossibility of rapid return and the complete absence of external events capable of refreshing the emotional background. A structured daily routine, alternation of work and rest, variety of tasks, all of this reduces monotony. Neuropsychological models show that a sense of control over one's environment and the predictability of what happens significantly reduce stress levels. This is accounted for both in ship design and in the preparation of those who will travel on it. Alternative approaches to the very concept of crew are also being considered. Hibernation, a state in which a person's metabolism slows substantially and the subjective flight time is considerably shorter than the objectively elapsed duration, is an attractive concept. In nature, similar states are observed in certain animals. In medicine, controlled hypothermic regimes are already used to protect the brain after acute trauma. However, long-term human hibernation remains a hypothesis. It is not known how organs and the nervous system will behave after years of slowing. A generation ship, in which the mission is continued by the descendants of the original crew, shifts the emphasis from biological to social risks, education, the transmission of knowledge, and the formation of cultural identity among those for whom the starship is the only world they have ever known, move to the fore. For such a scenario, a well-designed educational system and mechanisms for preserving scientific information over many decades are necessary. Regardless of the chosen strategy, an interstellar flight transforms the very notion of travel. This is not an expedition in the conventional sense, but a prolonged existence in an artificially created world, where every cycle of sleep and waking, every heartbeat, becomes part of a larger process of adaptation to an environment in which Earth has become a distant point on the celestial sphere, and daily life continues inside a metal hull, slowly gliding between the stars. And at last, after decades, perhaps centuries, the instruments begin to distinguish the light of an alien star system. The ship is approaching its destination. The approach to the Alpha Centauri system is not the arrival of an airplane or the landing of an automated station. It is a gradual, time-extended process, beginning long before the formal approach. Already years before arrival, the scientific instruments begin resolving individual radiation sources, refining orbital parameters, and compiling an ever more detailed map of the three-star system. The central pair consists of Alpha Centauri A and Alpha Centauri B, two bodies broadly similar to our Sun, orbiting their common center of mass. Apart from them lies Proxima Centauri, a red dwarf, the nearest of the three stars to us, and it is near it that a planet has been found with a mass close to Earth's, whose orbit passes through a region where liquid water could theoretically exist on its surface. These data were obtained from fluctuations in the star's velocity and changes in its spectrum. They give only an indirect picture of the planet, not allowing its surface to be seen directly. Deceleration of the ship is one of the most energy-intensive stages of the entire mission. If acceleration was accomplished by means of an external laser beam, braking requires fundamentally different methods. Magnetic sails interacting with interstellar plasma and gravitational maneuvers in the gravitational field of the system stars are under consideration. These processes stretch over months and years, gradually transferring the craft from a flyby trajectory to stable motion around the chosen star. The slightest miscalculation, and the ship either loses speed too early or finds itself in dangerous proximity to a star. Therefore, all actions are executed according to pre-prepared scenarios with continuous parameter verification and the possibility of corrections. The ship has reached another star system, and the first thing it does is not proclaim a discovery. It begins to measure slowly and carefully. Because science does not shout, it listens. After establishing a stable orbit, the phase of detailed investigation begins. As it approaches, direct observation becomes possible. High-resolution optical telescopes capture reflected light from a potentially habitable world, analyze atmospheric spectra, record thermal radiation. From the distribution of wavelengths, one can judge the presence of water vapor, carbon dioxide, and possibly oxygen and methane. Yet even such measurements yield no definitive answer regarding biological activity. These gases can form without the participation of living organisms, and any such signal demands careful, multi-level interpretation. Modern science possesses no universal biomarker that unambiguously indicates the presence of life. Combinations of indicators are used: unstable chemical mixtures, discrepancies between expected and observed gas concentrations, localized heat sources. Each such signal requires careful verification. If the mission envisions the launch of landing modules, an even more complex stage begins. The craft descend into the atmosphere, analyze the soil, search for organic compounds, measure isotopic ratios, data that allow the planet's history to be reconstructed and the question answered of whether it retained water for billions of years. For a crewed ship, the question of long-term presence arises. The possibility of deploying a base depends on the radiation environment, the availability of resources, and climatic stability. Even under favorable conditions, the first years are consumed by infrastructure deployment and adaptation. The human body and psyche again go through a period of adjustment, this time under the light of an alien sun. Communication with Earth, meanwhile, remains slow and fragmentary. Messages take several years in one direction, and any discoveries become known to humanity with a large time gap. This creates a particular form of scientific dialogue, in which decisions are made locally and their interpretation combines into an overall picture on the distant homeworld. Even if no signs of life are found in the Alpha Centauri system, the data themselves on planet formation, stellar evolution, and the behavior of matter under different conditions expand the horizons of terrestrial science. Arrival is not the conclusion of the journey. It is a transition from one phase of research to another. There is no clear finish line after which the task is deemed complete. There is only a change in the mode of work. A ship that has reached another star system becomes a mobile observatory, an extension of Earth's laboratories, carried beyond the boundaries of the solar system. It is here that the main meaning of the stellar arc is revealed, not only in the possible contact with a new world, but in the very expansion of human presence in the cosmos as a continuous process of observation, adaptation, and understanding. The journey to Alpha Centauri in this sense is not an expedition with a final point, but the slow inclusion of yet another part of the universe into the field of human knowledge, where every new signal and every measurement becomes part of a long conversation between the stars and those who have learned to listen to them. Please leave a comment telling me how this story resonated with you. I truly want to know whether it moved you. What do you think? If you had the choice, would you agree to set out on an interstellar journey, knowing you would never return? Or should humanity first send only automated probes? And also, do you find it more comfortable to watch in horizontal format or vertical for your phone?